Welcome back. So we consider yet another example on higher order derivatives. So this time around we are concerned with how to establish a proof of the general formula. So if we are able to get the nth derivative of a function, how can we prove that the nth derivative so obtained is true for all cases? We generalize the formula by observing the first few derivatives. So it is not a guarantee that it will always be true for all cases, even though we are reasonably certain it will be true. So there is a way to rigorously prove that it is actually true for all cases. So we may also be given a formula for the nth derivative, and then we'll be asked to prove that it is actually correct. So to establish a proof here, we will make use of a principle called mathematical induction. And this is typically used for establishing proofs having to do with natural numbers. So if we have a formula that has to do with natural numbers, that is assumed to be true or expected to be true for all natural numbers or for some set of natural numbers, then we will make use of mathematical induction principle to prove that formula. Okay, and so the approach to a proof or establishing something that a statement is true by mathematical induction is this. We will typically go through three steps to reach a conclusion as to whether the given formula or statement is true or not. The first is we establish that statement or examine or establish the statement for n equal to 1. Can also be for n equal to 0. If it happens that the formula applies for n equal to 0 or from n equal to 0 forward, okay, we've said before that natural numbers could start from 0 in some context, it could also start from 1. So if it happens that the first term, okay, for which the given formula or statement is true is 1, then we will establish it for n equal to 1. Okay, so this may be n equal to 1 or n equal to 0. So let's say n equal to n naught. All right, so which where this could be n naught could be basically it could be 0, it could be 1, or it could be any other term. Okay, it could be any of this. N naught is some element of this set. It could be 0, it could be 1, it could be 2, or any other thing. All right, so we'll establish it for the first term. That's okay. If we are given a formula, for instance, that the nth derivative of a given function y is some expression. So let's say that expression is some expression f of n. Then we will firstly find out if it is true for the first derivative. So we check if it is true for the first derivative. That's what we mean by this first step. Then after that, that is once we are able to verify that this is true, then we proceed with the second one. If we see that it is not true for the first term, then it can not be a correct formula anyways. We will have to stop there and say that the formula is wrong, all right? And so the second step is that is after having established this, that it is true for the first term, and we will say that we assume it is true for n equal to some m. Okay, that means we're assuming that if our n was some m, let's assume that it is true, that this particular statement is true for such a situation. And then this is just an assumption. We just state that okay, if this statement is true for some n equal to m, that means we are asserting that the mth derivative of y, for instance, if this is what we are trying to prove, where f sub n is some expression carrying n, then we are asserting that the mth derivative of y is equal to f sub m. Okay, that's an assumption. Then, based on that assumption, okay, this one now does not have to be, it's not that we are checking whether it is true or not, we are assuming it is true, okay? Having established that it is true for n equal to 1 or whatever the first term is, we're assuming it is true for some m, okay, for some m, which is also a natural number. Then, based on this assumption, we will now establish, that is, in this case, we are checking that it is true, establish that the statement is established that it is true for n equal to m plus 1. So after doing something like that, after using this assumption, after writing out this assumption, we'll make use of this assumption to establish that or to check that it is true for n equal to m plus 1. So for this situation now, it means we will be checking for the m plus 1 of y. That's the m plus 1 derivative. We know that m plus 1 derivative is the same thing as derivative of the m, okay, of y. So we'll take the derivative of this. We know the derivative of this already. So that means we will try to find out if this is equal to the derivative of f sub m. So we carry out this operation here and check that it is equal to the derivative of f sub m. So if they happen to be true, if they happen to be equal, that is, if that happens to be true, then we conclude that, so we just conclude that then indeed the given expression is correct, or the given equation is correct. So then indeed this the n of y being equal to fn is true. So that is how we carry out the mathematical induction proof, or proof by mathematical induction. We firstly check that it is true for the first term, whatever is the first term amongst the natural numbers to which the statement applies. Okay, we firstly check that it is true for that number. Once we are able to establish that, then assume it is true for when n equal to some m, and after that we will establish that it is true, that is also check that it is true for n equal to m plus 1. Once we're able to do this, then we can generalize that it is true for all n, okay, in the set of natural numbers as given in the statement. So the reason for this is that once we're able to check for the fact that it is true for n equal to 1 or whatever the first term is, and then we assume it is true for some n, and then we see that if we take n equal for some m, and if we take n equal to m plus 1, we also have it to be true. That means since we already know it is true for the first term, if we set our first term to be m, then I mean, since m here is arbitrary, so if our m was the first term, definitely by this we have also seen that it will be applicable to the second term. And if our m was 2, we also have seen already that it will be applicable to the third term, and so on and so forth in that order. That already assures us that it is definitely true for all natural numbers. So this is the idea. Whenever we have to prove any formula or any statement involving natural numbers, we can always make use of the mathematical induction. So to state this formally, we say that this is the principle of mathematical induction. So to put this formally, say that this is called the principle of mathematical induction. And this principle provides that we say let C sub n be a mathematical statement. Let this be some mathematical statement, okay, for n elements of the natural numbers. And now we say suppose the statement T1, suppose the statement T1 is true and assume and assume suppose the statement C1 is true, and that the statement assume that the statement C sub m is true, okay, for some m elements of n. We now say that then the statement then the statement C sub n is true for all n. Then the statement T sub n is true for all n elements of n, provided C sub n plus 1 is true. So this is just putting together everything we have explained already. So if Tn is some mathematical statement which applies to some n, okay, so it's a set of natural numbers, then we assume that, or suppose that the statement is true. That means provided that the statement is true for when n equal to 1. So in this case, the statement is starting from n equal to 1, or the statement is applicable for numbers from n equal to 1 upward. So we can start from n equal to 1. If it's a statement that applies to uh, numbers from n equals to 5 upward, we will have to firstly check that it is true for n equal to 5. So we'll just start from the starting point, okay, of wherever that statement is applicable to. Okay, so suppose it is true. So once we have verified that it is true for the first term, then we assume it is true for Tm, okay, which where m is some natural number. This is just some arbitrary natural number. We don't choose it. We just write m there. So we just assume it is true for m. Then we will establish that it is true for m plus 1. Once we are able to establish that, then we conclude that the statement is true for all n elements of the natural set n. So that is the principle of mathematical induction, and we will make use of that right now to solve some problem. So to see how this works. So we can so let's have this example now. So we say that we want to prove or show that the nth derivative, so we're still dealing with higher order derivative, shows that the nth derivative of y equals e to the power minus ax cos bx plus c is the ny equals r to the power of n, then e to the power of minus ax, then bx plus c plus n epsilon. So close the bracket where a equals r cos epsilon, b equals a equals minus r cos epsilon. So let me correct that. A equals minus r cos epsilon. B equals r sine epsilon, and r equals plus the positive root now of a squared plus b squared. So that is the problem. And having established that, we're now asked to hence show that the n of e to the power minus x sine of x equals root 2 to the power of n e to the power of minus x, then sine of 3n pi over 4, then plus x. Right. So this is basically what we want to do. So to show that all of this shows that implies or is synonymous to saying prove that the end derivative of this function is equal to this. This is the end derivative of a product of two functions. This is a product of two functions. The first part being e to the power of minus ax, the second part being cos of bx plus c. So we want to show that the nth derivative is given by this. So we will here make use of mathematical induction. So we say that we will solve this problem. Let's say that we want to get the solution of this. We solve this problem. We will make use of mathematical induction. We will prove by mathematical induction. So don't forget the statement as we provided for above. We said that we'll firstly check for the first term. Okay, we know that this is the nth derivative, and from knowledge of the problem, we know that we can have the first derivative, the second derivative, third derivative, fourth derivative, and so on and so forth. So we know that if we are dealing with derivatives, we should start from 1 unless otherwise expressly stated. So that means the first term to which this applies is 1. Okay, so we'll firstly check if it is applicable to the first derivative. That is, will this thing be true for the first derivative? That is what we'll check right here. So we'll go step by step as outlined above, as outlined when we started. We said that we'll be interested in what happens for n equal to n naught, that is the first term to which the general expression or general formula applies. Okay, we'll check if that works for it. Okay, once we have done that, then we'll proceed with the next step. All right, so the first thing is to check if this is going to be true, that is, if this formula will be the same thing for when n is equal to 1. So we now check that for the first case, we say let n equals 1. So if that is the case, by this formula above, we are going to have, then it will happen that the 1 of y will be equal to, that's when we set n equal to 1 over here, that will be equal to r to the power of 1 multiplied by e to the power of minus ax, then multiplied by this is bx plus c plus n. Our n is 1, then multiplying epsilon, then we close this bracket. So basically, this is telling us that for our first derivative, we should have r e to the power of minus ax into bx, um this should carry cos. That's an error in the question. This will be cos of this expression, please. Then why do wipe everything off? Let's wipe this off. So this is cos, multiplying cos of bx plus c plus n epsilon. Okay, all right. That should carry cos, please. That was an error. So let us correct that here. This is meant to carry cos, please. So let's correct that here. Wipe this off. This will carry cos of. So using this formula again, we're still using this formula. That will be cos of bx plus c. So that is still bx plus c, then plus n epsilon, then close the bracket. So that is what the first derivative will be. So this is what we get using the formula directly. Don't forget, our duty here is to check if this is true for when n equals 1. Okay, so we want to do that. I want to check if it is true for n equal to 1. We have just used the formula. We have not verified whether this is correct. We are just writing out what the formula provides first. So this is going to be cos of bx plus c plus n epsilon. So that is what we get from this. All right. So we can note that down. So this means that d1y is equal to this. So let's say that that is equation A, for instance. Then let us check. This is the function. Don't forget, this is the function itself. So let us check if we differentiated this function. Okay, if it would give us the same result as this, knowing that knowing what that r a is equal to this and b is equal to this and r is equal to this. So where we see n epsilon here, we already know how it came about is by making these substitutions. Okay, so let's find the derivative of y first. So we now say that is equation A. But for us to verify if this is correct, we know that our y is equal to the given function up here, which is e to the power minus ax cos bx plus c. So we write that out. We know that y equals e to the power minus ax plus, sorry, cos, that's not plus, please, cos, that's cos bx plus c. So from here, we can find out what the derivative would be. Derivative of this. Okay, the first derivative of this is the product of two functions. So we're going to use our product rule. So we take the first function. The first function is e to the power minus ax. We differentiate it by keeping this as constant. So when we differentiate e to the power minus ax, that will give us minus a e to the power minus ax. Then we keep this as constant. That will be cos of bx plus c. Then plus, for the second term, we will keep this as constant and differentiate this. So that will be e to the power minus ax multiplied by the derivative of cos. This derivative of cos of anything is minus sine. Okay, and then this is function of a function, so we have to multiply by the derivative of what we have inside. The derivative of bx plus c is b, because c is a constant. B is going to be the derivative of what we have inside here. So basically the derivative of everything put together will be minus b sine bx plus c. Okay, so this is what we get from taking the derivative of this, and that means this is our the y. So if we tidy this up, don't forget this is the y that we obtained using the formula. So if we are to verify that this formula is correct, that means we should verify or check if this expression here is the same as what we just obtained now. So let's try to tidy this up so that it looks like this. Okay, so putting this together, we see that what we have here right now is e to the power minus ax. E to the power minus ax is here, so e to the power minus ax is common to both of them. So this is going to be e to the power of minus ax. Then into, so we are factoring that out of this expression. That's the only thing that's common to both of them. So this one is minus a. That is, from here we have minus a left, and we have cos bx plus c. Then the next thing we have here is plus, sorry, this is minus, still minus. This is going to be minus b, and this is sine bx plus c. This is sine bx plus c. And then we close the bracket. So that's what we're able to get from this. But we can see that here we have R. So here we don't have R. And then the question provides what R is, or how we came about R. We can see that when we have A A is the same thing as minus r cos epsilon, and B is the same thing as r sine epsilon. So we can make that substitution here. So we know that we can say that given that A is equal to, we're told that A is equal to minus r cos epsilon and B is equal to r sine epsilon. So from this, we can simplify this expression. Okay, so then we can say that going further with this, dy will be equal to e to the power of minus ax into minus a right here. Since a is equal to r cos epsilon, then minus a will be, sorry, since a is equal to minus r cos epsilon, then minus a will be minus of this. That is just r cos epsilon. So basically what we have here is r cos epsilon, then that is minus a, then multiply by cos of this, that is cos of bx plus c. Then we have b here. B is r sine epsilon, so this is minus of r sine epsilon. Then what we have here is multiplied by sine bx plus c. So this is everything we have now. And doing this, we now have something that is common to both of them. Again, we have r to be common to both of them, so we can move out r. Don't forget, we are trying to work towards this expression, that is to verify or actually check that this derivative is actually equal to what is provided for by this formula when we substitute n equal to 1. Okay, so we can see that now r is common to both of them. So obviously we can move out r so that we will have a pattern similar to this, but this is going to give us r into e to the power of minus ax, then into cos epsilon cos bx plus c, then minus sine epsilon sine bx plus c. So that is that. That's what we have inside. Now comparing this to this. So we didn't substitute n equal to 1 here. Sorry, that's an error. So this is n equal to 1. So this is meant to be 1 multiplying epsilon. Okay. So this is just epsilon. Alright. This is just epsilon. Bx plus c plus 1 times epsilon. That will give us this epsilon. Right. So now going further with this and comparing again, we see what we have here is bx plus c plus epsilon, but here we have cos of this minus cos of this, so we can see that this is cos of bs plus c then plus epsilon. So, and we recall that if we're using from our trigonometric relations, we recall that cos of a plus b, okay, we've used this formula in a previous lesson, is equal to cos a cos b minus sine a sine b. So basically what we have here, you can see is cos epsilon cos this, so the coefficient, I mean the arguments are similar. This is cos epsilon, this is sine epsilon, this is cos bx plus c, this is sine bx plus c. So then we can say that our cos epsilon cos bx plus c is going to be minus sine epsilon sine bx plus c is going to be equal to the addition of the two. So in this case, just comparing with this portion, we see that our a is just equal to epsilon and our b is equal to bx plus c. Okay, or say a is equal to bx plus c and b is equal to this, doesn't matter. So that is basically equal to cos of a plus b. That will be epsilon plus bx plus c. So, and of course, by simple rearrangement, that is just the same thing as cos bx plus c, then plus epsilon. So that is that about the first derivative. We can see that this expression here is the same thing as cos bx plus c plus epsilon. So we can say that therefore, okay, what we have up here is dy equals Putting this here, this will be r e to the power of minus ax. Then we have this expression altogether as cos bx. So this is cos bx plus c, then plus epsilon. Close the bracket. So let's write this properly. So this is bx plus c plus epsilon. So comparing it now with equation A, we can see that it is the same thing as what we have in equation A. So I've been able to establish that by working on this itself. So we have been able to see that by differentiating this, okay, using our usual uh, process of differentiating a product, we have seen that the derivative is the same thing as what is provided for by the formula when we substitute edge n equal to 1. Okay, so and that means that indeed the formula or the statement is true for n equal to 1. So we say that, and so this is our equation B. So by this result, we have been able to see that the statement is true as the given statement that the nth derivative is given by the formula provided is true for n equal to 1. So I've established that. So we'll proceed now with our mathematical induction. So to proceed again, we now assume it is true for n equal to m. So I've established that it is true for n equal to 1. This is the first term to which it applies. Okay. That's the first thing. So since we have verified that it is true, then we now proceed. If we tried this and it wasn't true, then we would not be able to proceed with the solution. All right, we'll just conclude that the given statement is false. All right. So we check for the second step now. So assume it is true. Assume the statement is true for n equal to m. So if that is the case, that is our dm, that is the mth derivative of y for the given function, will be equal to, as provided for by the formula, we'll just set n equal to m in the formula. So this will be r to the power m e to the power of this blah blah blah, then this will be cos of m epsilon. So this will be to assert that this is the same as r e to the power of minus ax, then cos of bx. So this is r to the power of m, sorry. So this is r to the power of m. And this is cos bx plus c, then plus m epsilon. So that's basically replacing n by m, okay, wherever we add it in our formula. So this is an assumption that we will now use in the third step. That means mathematical induction will mean that we want to reach a conclusion on what m plus 1 derivative will be by taking in this result for the mth derivative. That's the first, that's the next thing now. So we now say that for n equal to m plus 1, what will happen? The derivative of this will be the m plus 1 of y. And we will now check what will the formula give us. If we actually just use the formula directly, we will get something like r to the power of m plus 1. That means wherever we add n in the formula, we will replace it with m plus 1. So this step 3 is similar to step 1 in that we are doing two things. The first is use the formula, okay, substitute n equal to 1 in the formula. Then the second is then do the derivative normally to see that it is the same thing as what is provided for by the formula. So that's basically what we are doing here. So the first thing is we are substituting m plus 1 into the formula directly. So if we are substituting m plus 1 into the formula, we will obtain this expression here. We will obtain r to the power of m plus 1 e to the power of minus ax cos of bx plus c plus this will be m plus 1 epsilon. So that's basically what we are writing out first. Okay, just like in the case of for n equal to 1, we substituted n equal to 1 first in the formula. Then we did the derivative normally to check that they are the same. So that's basically what we want to do here. Substitute into the formula normally for n plus 1, then do the derivative normally to see if the two will be the same. So this will be r to the power of n plus 1, then e to the power of minus ax, then multiply by cos of bx plus c, then plus this is m plus 1 epsilon. So we close the bracket. So we can call that equation D. So we now want to check for what happens. So we now say that, but when we differentiate normally, we expect that the m plus 1 of y simply means differentiating again what derivative at the mth point is. And this is where our equation C now comes in. This is where this assumption is used. It is this assumption in the second step that we will employ here or deploy here to verify that it is true for m plus 1. Okay, so if it is, since we have assumed that it is actually it is, we're going to make use of that here. So we expect that from equation C, now from equation C, it will follow that the m plus 1 of y will be equal to the derivative of, so we substitute the derivative, the mth derivative as provided for by equation C. That will be r to the power of m, then e to the power of minus ax, then cos of bx plus c plus m epsilon, then close the brackets right here. All right, so that is that about that. And so what do we do going forward from here? We will now do this derivative normally. We will carry out this derivative. We can see that what we have here is r to the power of m. R to the power of m is a constant, so it does not affect our differentiation in any way. Only the portions carrying x is what we have to deal with. So we can move out r to the power of m if we like, and then take the derivative of what we have left. So this is again derivative of a product of two functions. The first part being e to the power of minus ax, the second part being cos bx plus c plus m epsilon. C and m epsilon are some constants. So basically the derivative of this argument is just b as before. So this is going to give us r to the power of m. That is a constant, so we can move it out. Then the derivative of e to the power of minus ax, that will be minus a e to the power of minus ax. That is differentiating this. This is product to differentiate this, multiply by this. That is cos bx plus c plus m epsilon. Then differentiate cos of this. We know that the derivative of what we have inside is b, and the derivative of cos whatever is minus sine whatever. So this is going to be minus b sine whatever we had inside, bx plus c plus m epsilon. All right, and then we multiply by this. We have taken the derivative of this, then multiply by e to the power minus ax, e to the power of minus ax. That is kept as constant. So this is everything we get from this derivative. And again, to simplify further, we will say that this is going to be, of course, we can see that e to the power minus ax is common, so we can move it out of the bracket. So this is going to be r to the power of m, e to the power of minus ax, that is moving this out, and then what we have left will be minus a into cos bx plus c, sorry, plus m epsilon, bx plus c plus m epsilon, close the bracket, then minus b into, so we've moved this out already, so this is what we have left, minus b into sine bx plus c plus m epsilon, then close the bracket. All right, so now we're good. Again, to move forward from here, we identify a as given or provided for in the problem, just as we did here. We know that a is minus r cos epsilon and b is r sine epsilon. That is provided for in the question. Okay, we have that right here. So we're going to do the same thing here. So working on the same problem, we will see that this is equal to, let's start the equal to here so that we have enough space. This is equal to r to the power of m e to the power of minus ax into, this is r cos epsilon. Since a is minus r cos epsilon, then minus a will be r cos epsilon, then multiply by cos of bx plus c. Okay, this is bx plus c plus m epsilon, close the bracket. So let's write that epsilon properly. So this is epsilon, then b is r sine epsilon, so this is minus r sine epsilon into bx plus c, then plus m epsilon, then close the bracket. So basically this is what we have left. We can now see again that r is common to both of them, so we can move out another r. This will be r multiplying r to the power of m, then multiplying e to the power of minus ax. Then what we have left inside can be written as cos epsilon cos, okay, cos bx plus c plus m epsilon, then minus sine epsilon sine, sorry, this is sine this is sine, please, this is sine something, sine bx plus c plus epsilon, please. So it is b that was sine epsilon. Okay, so this should still have sine of bx plus c, then plus m epsilon, then we can close this bracket. So with this we have sine epsilon sine bx plus c plus m epsilon, so we can close the bracket. All right, so now we're good to go. Again, we can identify the fact that this is just like we did for the first case. This is the same thing as having cos a plus b. All right, so we can just add everything up. So this is going to be equal to cos bx plus c plus m epsilon, then plus epsilon, because that is exactly what we have here again. Okay, so this is going to be equal to r multiplied by r to the power of m, that will be r to the power of m plus 1, and this will be e to the power of minus ax, and then this will be the same thing as cos epsilon plus bx plus c plus m epsilon. So that will be everything we have here. So because cos epsilon plus cos of this this whole thing here will be, by our formula, it will be cos epsilon cos this, that will be, if we take this as our a and this as our b, that will be cos a cos b, that's cos epsilon cos this, minus sine a sine b, that's sine epsilon sine this. So basically we have been able to identify this expression as being equivalent to this using that formula that we wrote up here, using that again and using the same approach as what we did to simplify this one earlier. All right, so going further now, we can identify that this is equal to r to the power of m plus 1 e to the power of minus ax, then multiply by cos of this expression. So we can see this is basically cos of bx plus c plus m epsilon, then plus epsilon, that is the same thing as cos m plus 1 epsilon. So we close this bracket. So basically, this is providing that the m plus 1, this is the m plus 1 of y is equal to this expression. And if we compare this with what we obtained by using the formula in equation D, we see that this expression in equation D is exactly the same thing as what we have now verified here to be the m plus 1 derivative. So that is the idea. That means by this observation or by this result, we have been able to establish that the statement is also true for n equal to m plus 1. And that tells us that it is indeed true for all natural numbers. Because even if our m was 1, okay, it will be true because we have basically established that here. So it means that for m plus 1 also, that's for instance 2, it will also be true. If we take m to be 2, it will also be true for m plus 3. So from this, we are able to conclude that indeed it will be true for all natural numbers. So we can identify our equation E. So going by equation D and E, we have been able to say that the one provided for by the formula, okay, the one provided for by the formula, which was this, is the same thing as what we would have obtained by differentiating the mth derivative. So by that, we verify that the function is indeed, the statement is indeed true for n equal to m plus 1. So we say that thus the statement given or provided for in the problem is true for n equal to m plus 1. And so then by our principle of mathematical induction, we can conclude that this statement is true for all n, okay, elements of the set of natural numbers. All right. Hence, the statement is true. So we can say that the ny, that's the statement, I'm just writing the statement, is indeed equal to r to the power of n, e to the power of minus ax, cos of bx plus c plus m plus 1 epsilon plus m plus 1, sorry, plus n epsilon, sorry, please. That's the formula we're given, plus n epsilon. And this is true for all n elements of n. So by this, we have completed the proof. So we have proven that it is indeed true for any natural number n. Why? Because we have seen it is true for n equal to 1. We have also seen that if we take an arbitrary m, it will be true for m plus 1. So if our m is any natural number, then it will be true for the next natural number. So if since we have seen that it is true for the first one, which is 1, definitely it will be true for the next one, and the next one, and the next one, and so on and so forth. So that's the thinking behind the principle of mathematical induction. And so we've completed the aspects of this problem that has to do with us establishing that the given formula is correct. Okay. So let us now examine the second part of the problem. The second part of the problem asks for the derivative. It asks us to show that the derivative of this, that's the n of e to the power of minus x sine x equals root 2 to the power of n e to the power of minus x, then sine of 3n pi over 4 plus x. So going into the, that's basically the second part of the problem. The problem says that having established that, it says hence show that this is equal to this. So we are going to make use of this result, which we have now established to be true for n, for all n. So we will just make this function that we need to get its nth derivative term to be similar to this, so that we can compare and obtain the values of these constants b, r, a, and epsilon, so that we will use the formula directly to obtain whatever the derivative of this is going to be. Right, so let's go ahead and do that now. We will have to write this function in such a way that it is similar to the function we have up there. So for rough work now, not part of the solution, so some rough work. We know that the given function, which we just established its derivative to be equal to this, was actually e to the power of minus ax cos bx plus c. Okay, and we obtained its derivative to be equal to this. All right, so now we have something similar. So let's say that that is y, so let's call it y star. Then we know that the derivative of the function that we want to get its own derivative now is e to the power of minus x multiplied by sine x. So to go further, we will say that we will have to write this function in a form similar to this. So to have that in this form, we know we have to change this sine x to cos of something so that we can compare directly with this and obtain what its derivative will be by direct comparison with this. We don't need to differentiate from the ground up and begin to examine what the pattern is going to be. That will be a waste of time having established this already. So we go ahead to say that, okay, if we have sine x and we have to write it in terms of cos x something. So we can see this should serve as a guide for us. We can see that x is positive right here. And we can see that in the derivative of this, now look at this one has cos bx plus c, and in the derivative will have cos bx plus c also. So that means that we should try to find an expression for this. Instead of having cos, we should be sine, and the argument should have something like x something. Okay, so we know that normally sine x is equal to cos 90 minus x. We've talked about that before. That was cos pi over 2 minus x. We also know that if we have cos of minus x, okay, cos of minus x is the same thing as, let's write this properly, cos of minus x is the same thing as cos of x. So basically we can multiply this by negative. So it means that we can also say that sine x is equal to cos of the negative of this. That will be x minus pi over 2. So however it is written, it will give us the same result. So we can write sine x as cos x minus pi over 2. Why do we choose this ahead of this? Because this has positive x, just like the argument we have here has positive x. You know that we've said this several times that when we want to establish something, we have our destination in mind. That is, we look ahead while solving so that it will reduce our burden as much as possible before we get to where we need to make use of this result. All right, so we can now say that this will be equal to e to the power of minus x multiplied by cos of x minus pi over 2. So that will be our function. This is the function we have to deal with. So we can now compare it with this original function. So we now say that by comparison with y, which is equal to e to the power of minus x into cos bx plus c. We'll be able to identify what these constants are, so that when we are making use of this formula, we can know what exactly to substitute into them. And this is going to give us this expression. This is going to give us, from this we will obtain a is the coefficient of x in the power of e. So this is coefficient of x here, this is minus x, this is minus ax. That means a is equal to 1 for this situation. Then b is the coefficient of x in this expression. We can see b is equal to 1 as well. So b is equal to 1. Then the next thing is, I think that is all we can get from here. What is C? C is this constant written together with bx. So this is bx then plus c. So we compare this with this, we see that our c is minus pi over 2. So that makes it easy to deal with. And then we also have in our derivative r and epsilon. So we can get r and epsilon from the expressions provided for. So from the details of the question, we know how to get r and epsilon. R is given by this, we say that A is equal to minus r plus epsilon, b is equal to this, and r is equal to the square root of a squared plus b squared. So we already know a and b, so we can just use that to get r and epsilon. So let's go ahead to do that now. So we use that right here. So I've been told that r equals the positive root of a squared plus b squared. So this will be equal to the root of our a is 1 plus our b is also 1. So let's put that here. And that will be the root of 2. So we'll leave it at that. And then the next one is our epsilon. So we know that a is equal to r cos epsilon, sorry, minus r cos epsilon. That's what we are given the question. So a is minus r cos epsilon. So from here, that means 1 is equal to minus root 2 multiplied by cos of epsilon. And we also know that b, okay, b is equal to r sine epsilon. That means b, which is 1, is equal to r, which is root 2 multiplied by sine epsilon. So if we divide both sides of these two equations, so let's say this is some equation 1 and equation 2. If we divide equation 2 by 1, so let's say that this is equation 2 divided by equation 1. What will that give us? We're going to have 1. Okay, 1 will be divided by 1 on this side, and then we have root 2 sine epsilon divided by minus root 2 cos epsilon. And at the end of the day, we're going to have root 2 cancel root 2, and this will be sine epsilon over cos epsilon, which is tan epsilon, and minus to that side will be equal to minus 1. So basically, we're going to have this to be epsilon will be equal to the tan inverse of minus 1. So tan inverse of minus 1, let's check that with our calculator. Tan inverse of minus 1. Tan inverse of 1 is 45 degrees, which is pi over 4. So for minus 1, it should be minus pi over 4. So expect this to be minus pi over 4. Okay. We can also add, to make it positive, for instance, we can also add 2 pi to this expression. So if we add 2 pi to this, 2 pi to pi over 4, or say add pi to it, we know that this thing is negative. So if we want to get a positive result, we will observe that. So basically, what we are driving at is the fact that we could just leave this the way it is. We could leave it as minus pi over 4. That is fine. We are not given any restriction as to whether epsilon should be positive or negative. Okay, so there is ordinarily no need to just work further with this. However, we see that for this particular situation, we are able to also see that for the destination we are driving at, we have n, we know that in the derivative, we should have n epsilon, okay, when we look at this argument. Now forget about this cos and sine first. If we look at the argument, we have n epsilon, and in this case, that means epsilon is being, epsilon would be predictably 3 pi over 4, okay, or something like that. So if we have minus pi over 4, it will probably not give us the same result as what we want to have in the argument here. So let's see if there is a way we can modify this without disrupting this property and still have 3 pi over 4. So that's the idea. That's what we're trying to do now. So we know that that will be that for us to get 3 pi over 4 from this, we'll have to add pi to it. And if we add pi to it, what should that do? We know that from our quadrant of angles, we have cast, CAS, Phi. So we know that on the third, this is first quadrant, all of them positive. Second, only sine is positive. Third, only tan is positive. Here, only cosine is positive. So if we have this expression, we know that on the third quadrant we actually have 180 degrees plus theta. So if you add 180 degrees to an angle, it doesn't change its tangent. So that's basically what we are going to do here. We're going to take advantage of that part here and add 180 degrees to this angle that we just got. 180 degrees is pi. So we can add pi to this expression and it will give us the same results. So we can easily verify that. So for this now, we want to get the tan inverse of minus 1. That will be shift tan inverse. Then we'll put in minus 1, close the bracket. It will give us minus pi over 4. So if we add pi to it, plus shift pi to give us 3 pi over 4. And basically that is the same thing, because if we check the tan of 3 pi over 4, that's the answer we just obtained now, it is also equal to minus 1. So if we add 180 degrees to the angle, it doesn't change the value of the tangent. So we can say this epsilon is equal to minus pi over 4 plus pi, just to have a positive angle. And this is going to be equal to, if we put this together, this is going to be 3 pi over 4, if you like. So with this, we are good to go. We can now use our formula. We know R already, we know A, we know B, we know C, we know R, and we know epsilon. So we have all the entities that we need to write out the derivative of this function, okay, using this formula. So then we now say that therefore uh, the nth derivative of y star will be equal to, so let's write out this formula, this general formula that we have verified already, equals r to the power of n, r to the power of n, e to the power of minus ax, then cos of bx plus c plus n epsilon. Okay, so that's what we have up here, e to the power of minus ax cos of bx plus c plus n epsilon. So we now compare this now with this. We see already we have been able to establish all the constants, so we know it is going to give us the same result. So basically this is going to give us r. Our r is root 2. We have that right here, so we can put that in. This is going to give us root 2 to the power of n. Then we have e to the power of minus ax. So we've seen that a is equal to 1. So this is going to be e to the power of minus 1x. That is e to the power of minus x. Then we have cos of bx plus c. So we see that our b is 1. So this is going to be 1x. That is x. Then plus c. Our c from up here is where is c again, minus pi over 2. So this is going to be minus pi over 2, then plus n epsilon. Our epsilon we've been able to see is 3 pi over 4. This will be n multiplied by 3 pi over 4, and then we can close the bracket. So basically this is everything we have here, and by tidying this up, we know that our final expression that we want to establish is carrying sign as well. But we have already established that when we have sine x, there's the same thing as cos x minus pi over 2. So we can just let go of this. So if we have cos and minus pi over 2, we can let go of the minus pi over 2, and what we have left, we take the sign of it. So basically this means that what we have here, if we were to tidy this up, this will be root 2 to the power of n, e to the power of minus x, then cos of, so we can put all of this together. This is x plus n 3 pi, or 3n pi all over 4, then minus pi over 2. So we already know from what we wrote up here that sine x is the same thing as cos x minus pi over 2. So that means sine, we're using the same result here. So let me write it out again. We know that sine x is the same thing as cos x minus pi over 2. So in this case, our x is the sine of this minus pi over 2. cos now, cos of this whole expression minus pi over 2 will be equal to the sine of just this expression. That is, we can ignore the minus pi over 2 and replace it with sine. So basically, this is going to be equal to the root of 2, the power of n, then multiply by e to the power of minus x, then multiply by sine of. So we have changed from cos to sine. So just like we are changing from cos to sine here, that means we ignore the minus pi over 2 portion. This will be x plus 3n pi over 4. We ignore the minus pi over 2 portion. And that is that about that. So let's write this off. So therefore, we have our result. That means the n of y star, which is what we have up there, is going to be equal to this using the results we established earlier. So that is that about that. It's quite easy now to see that this function will have its derivative, its end derivative to be equal to this, and that is basically what we were asked to establish in the problem. Okay, that's what we were asked to show, that this expression is equal to this, and 3n pi over 4 plus x. So we have x plus 3n pi over 4. That is just the same as this. So that means now we have been able to establish that indeed derivative of e to the power of minus x multiplying sine x is the nth derivative of this is simply root 2 to the power of n e to the power of minus x multiplied by sine of x plus 3n pi all over 4. And that is that about that. So for your exercise, you can also play around with the fact that this is true. You can also play around with having to establish this using the what do we call it now? The principle of mathematical induction that we employed earlier to establish the one originally given. So you can also use it to play around on this and see that it is actually true for n equal to 1, assume it is true for n equal to m, then also establish that it is true for n equal to m plus 1. So please do that as an exercise. That is the end of this lesson. Thank you for watching. We'll proceed from here in the next lesson.